So today we're going to get started with some motors and controls. We're going to be dealing with, it's kind of along the lines of electricity because we're using electricity to kind of do different things. But, rather than just, putting in plugs or, wiring up lights for switches to do different things, we're going to kind of take a little bit step further and, kind of how we utilize electricity, and especially how we utilize it in a shop, because we do utilize electricity quite a bit to do a lot of different things that we do, as long as we're not like dealing with like hand tools. And so we're going to talk a little bit about motors and controls today. So we've got some magnets that are on the bottom side of these things, and these magnets, they're not just any regular magnet. And I'm going to kind of show you some things. We're going to do kind of like three different little I guess science experiments with these things to kind of leads into our motors and controls. But these magnets are what we call neodymium magnets. They are rare earth magnets. They are super strong. As compared to, a regular, where's my stuff at? As opposed to a regular magnet like this that you would probably have like on your refrigerator. These ones are pretty weak magnets in comparison. These ones are super strong. If I were to put down a little paper clip, you can see how quickly and how fast those things kind of pull that paper clip. Where if I just take this regular one, notice it doesn't have quite the same pull. So these little rare earth magnets, right? Super strong. Hard to pull them apart. I've got like a whole bunch of them that are right here. They're tough to pull apart. They're super strong, right? And you can pull them apart, but we're going to leave them together for kind of our example here of what we're going to do. Now, when we think about like motors and controls, pretty much every single tool that we have in a welding or in an ag mechanic shop is going to have some sort of motor that's going to be on that. And that's kind of what we're going to deal with today, is kind of understanding how those motors work and how they function. And magnets are actually a really big part of how motors function and how they operate. And I'm going to show you, I'm going to switch my other camera here real quick. So I'm going to show you guys, oh my gosh, my magnet is sticking to my mic. Okay. If I have these little rare earth magnets and I were to drop these things, you can see that they drop at a pretty consistent speed, right? I mean, it's pretty quick, maybe a second from it to drop from my hands up top and hit down below. And that's just gravity, right, taking effect. But if we were to take these magnets and we were to drop them inside of a copper tubing, this thing is just a hollow tubing. There's nothing like blocking on the inside. This is something we would use for like plumbing, right? Because this stuff is made out of copper and this magnet doesn't actually stick to copper at all. But because it has copper, it will actually induce an electrical current. We use copper for the wiring when we do electricity and all that kind of stuff. And as we take this magnet and if we were to drop this thing on the inside, that movement is actually going to create an electrical magnet, like a magnetic field that is actually going to slow down this magnet. And so what we're going to do is we're going to drop this thing on the inside here. I'm going to try to get the view. We're going to drop this magnet on the top side right here. Make sure there's one side that it gets caught up on because there's a little burr. So we'll drop it on this side. So if I were to drop that, you notice that that speed of this magnet gets slowed down dramatically. You saw it drop right there. This kind of principle of basically this dropping magnet and the copper tubing that's on the outside of it, what it's doing is it's actually taking this magnet and it is slowing that magnet down because it's creating a magnetic field that is essentially grabbing onto those magnets as it's dropping, as it's moving, and it's slowing that process down. Again, there's nothing fancy. This is literally just a copper tubing pipe. And it's just this neodymium or these rare earth magnets that we're dropping through. You can get these things. I bought these ones at Home Depot. They're a couple of bucks for these things. You can buy them there. The one thing with these is that they're brittle. If you drop them, if they hit the ground, they're going to shatter. Unlike a regular magnet that you have, for like a refrigerator or something, those ones are not going to be, as brittle as these rare earth ones. But you can get these things. You can get a piece of copper tubing. You can try that out, and it's pretty cool. But what it ties into is, the fact that electricity and magnets really kind of coincide with each other. I don't know what the term I'm looking for is, but they work with each other. For a motor to work, we have to have that magnetism. We have to have that electricity kind of in conjunction with each other to get a lot of processing and a lot of work done. If you think about, bandsaws, think about drill presses, think about, any of the drills and different things that we have in the shop. Anything that's going to use a motor is going to be using magnets and it's going to be using electricity. Now, some of you may have seen, well, you may not have seen this before, but you may have seen something similar to this. Okay, this right here is just a little, piece of mild steel that's kind of sharpened down to a point. We actually use these things as a little cold chisel. They don't work very well, so that's why I just kind of grabbed this one and I wrapped some little copper wire around this thing. And you'll notice I'm going to kind of switch my camera. I'm going to go to the other view here. And you'll notice we've got, a little paper clip here. And I've got this little iron core wrapped with copper wire. And notice it's not doing anything. If I were to take, though, and attach a battery, get my battery here. If I were to attach a battery to both ends, the positive to one, the negative to the other, what I'm going to end up doing is actually creating an electromagnet. Now I've got that electricity that's flowing inside. You'll notice that thing picks it up. Sometimes there's a little bit of residual magnetism left in. That's why it's kind of sitting there, kind of connects. But now it's not as strong, right? It's not as strong with that battery. That battery's disconnected. If I were to connect that back together again, oh man. Now all of a sudden, this thing is a magnet. So it's pretty cool because we can take stuff like this and we can create electromagnets. And we use these things quite a bit for some of the controls that we have with motors. We'll talk about those things in just a second, but we create electromagnets, maybe not in this same kind of form, in this same design, but we can create a magnet simply by taking an iron core, wrapping it with copper, and then introducing electricity into that system. Okay, and this magnet, it's not really strong, but it is a magnet and it will kind of pick up stuff. The tighter the windings, the more windings you have, the bigger input of electricity you have, the stronger that magnet's going to be. If you've ever been to like a junkyard before, where you've got these big kind of like crane things that have like a little circular disc, that's going to be a magnet, but it's not like a stationary magnet like you would have like one of these or like a neodymium magnet. It is an electromagnet, meaning that if you introduce electricity, the magnet turns on, you turn the electricity off, that magnet turns off. And so the nice thing with that is you can kind of control that electricity, you can control that magnetism, and we can do that to kind of create different controls and stuff. We're going to take these same magnets, okay, right now, we've kind of created a little electromagnet with this thing. We're going to take these same little neodymium magnets, and we're going to attach a battery to the bottom of this thing. And what we're going to do here is we're just going to create a very simple motor. And with those electromagnets, with that, battery there, and this little copper kind of jig that I've kind of created, this is going to touch the very top of the battery. These are going to kind of be, as close as we possibly can. We ideally don't want those things to touch those neodymium magnets. You can see that little round portion right there. And what that'll do is that creates an electromagnetic field. So now we can take this thing. If we take this little jig that we've made up, we can set that thing on top and you'll notice that thing starts spinning. This is a very, very basic motor where we've got some magnets, we've got the electricity with the battery, that little wire that's actually spinning around, that's what's actually kind of conducting the electricity and getting these things to spin. Now you'll notice this thing is spinning this way, right? We can take these magnets, and magnets all are going to have north and south poles. I can simply take those magnets off. I can flip them around. I can put it on the bottom side, and I can actually get this little motor that we have working to turn in the opposite direction. Now, sometimes if you have less friction, this thing is actually touching a little bit. You'll notice it's kind of speeding up as we're going. That is actually, the less friction or the closer you get without actually touching it, okay, is going to get that motor to spin a little bit faster on this very basic motor. There are some different things that we're going to do when we actually talk about the bigger motors that we're going to deal with. And kind of how we can adjust the speeds of those motors, how we can adjust the rotation and different things there. But using magnets, using electricity, we can create simple motors. Now, this one is not really going to work very much. We can't really transfer this power to anything. This is more of just, why'd you stop? This one is more of just kind of like, kind of shows some of the concepts and some of the basic principles, of electricity. When we get to a motor that we actually want to run, we got to have something that's going to actually deliver our power to us. So we're going to go through, and I'm going to kind of get off of this one here. You can see that thing wants to keep slowing down. It keeps getting caught. Anyway, we'll go ahead and we'll get off of this right now. You can let that thing sit, and it really does sit. Sometimes if everything's set up, it'll just spin really fast and kind of move around. But we're going to go through a little PowerPoint real quick on some electrical motors. Electrical motors and controls, obviously, we're going to use these things in the shop. They are going to be on almost every single tool that we have inside of the shop. And so understanding how to, match these things, how to identify, how to, be able to like read the plates, that's kind of what we're going to be dealing with today with our little activity is kind of important. Okay. We can use these things in a lot of locations. We can make things to where they're automatic, where you don't even have to do things. You can make them really small. Motors typically aren't going to fail, right? There's not a whole lot that's typically going to fail on these motors, so they last a long time. We can make motors quiet when you think about like washing machines and different things. Some motors are really loud, some of them aren't. They're very simple, they're very easy to operate, doesn't take a whole lot of training, and they're able to use power to where we can make cuts and we can make bends and we could do different things, without having to put a lot of power into that stuff and physically doing things. We can basically let the motor do the work. So when we're selecting motors, kind of some of the important things that you need to make sure that you're kind of aware of is what kind of voltage input that motor is going to require. Is it 120 volts? Is it 240? Is it 480 volts? And there are nameplates that you'll see at the end of this PowerPoint that are going to kind of explain that, and you guys are going to learn how to read those nameplates. Pretty easy, not too difficult for the most part. This information is just labeled on there. So if you're replacing a motor that did fail, you basically want to find that information, and then you can match a motor that's going to meet up with that. Is it single phase or three phase? This has to do with the electrical input as well. We'll talk a little bit about what those things are later on here. What power is required? Like what horsepower is it? What speed does the motor need to run at? Those things are important when we're actually making sure that we have the right motors on our. I'm going to turn my motor off. My motor's getting kind of annoying. Anyway, what horsepower, what speed, and the other thing, this is probably maybe not as critical, but like what kind of bearings do we have? What kind of frame? I mean, the frame, I guess, is pretty important because if you're going to mount that to something, there are different mounting points, different brackets, different things. And so when you're replacing those things, that's important. We're really not going to deal with that. We're not really concerned, with that. We're more worried about what kind of power is coming in. What power is it using? What's the horsepower? What's the motor speed of this thing? That's more of kind of what we're looking for. So kind of like that little simple motor that I showed you, this one is kind of an illustration that shows a little bit, maybe a little bit better, on how we can actually transfer this power. So in a simple motor, what we're going to have is stationary magnets. We're going to always have a north and a south pole on these magnets. And what happens essentially is this little middle portion, or this rotor that would be on the inside, that is going to be rotating. So you're going to have this housing that's going to be around. It's going to have magnets. It's going to have a north and a south pole. And what's going to happen when we do is we're going to energize this thing. And that little spinning rotor right there is going to have opposite. It's going to kind of rotate both north and south poles. And what that's going to do, if I had this bar, and I can't get this thing to stop. If I had this bar that was kind of lined up with, I'm trying to think of how I can best describe this here. If I have that, I wish this thing would stop. If I have this end right here, this thing that's spinning, okay, you notice this little rectangle. One end is going to be a north pole, one end is going to be a south pole. And if you know anything about magnets, if we were to kind of flip these things around and we had these poles kind of opposite, both the, south and north poles, they're going to want to repel each other, right? So they're not going to want to be next to each other. if they, well, I guess if it's the same, right? So if you have two North Poles, they're going to repel each other. And they want to find the North Pole wants to line up with that South Pole. Okay. If they go opposite, you're going to get that resistance. If you've ever taken two magnets and try to push these things together, okay, it's really difficult to do that, especially, I'm going to stop this share right now. If I take my neodymium magnets and I try to push them, I have these poles that are opposite. And so what it's doing is it's actually pushing a force and it's kind of forcing these things away. What a motor is doing is it's essentially taking that rotor, and you have your stationary magnet here and you've got that rotor that's on the inside, and it's basically putting the north poles together. It's matching them up and it's wanting to repel. But now it's not going to push it back because it's, it's on a shaft that's not going to allow it to be pushed back. And so what it's going to do is it's going to want to move up or it's going to want to move down. And what that's going to do is it's going to cause a rotation. And as that rotates and it's going to rotate around, it's going to try to hit that south pole. But what happens on that motor is we actually flip those poles as that rotates. So we're always going to have the north pole facing the north pole, and we're always going to have the south pole facing the south poles because it's rotating that power as we're actually going through. And let me share back in here. It's rotating this thing around and just switching those north and south poles. The stationary magnets on the outside, those are never going to change. Those are always going to be north. They're always going to be south. And so that's what's going to creating that rotation. That's kind of what we had on that on the rotation on that very simple motor there. We're basically having these forces. We're creating an electromagnet and we're causing those forces to basically repel each other and then cause this spinning action. If we look at a real basic motor, most motors are going to have a lot of these very similar things. They're going to have this rotor that's going to be on the inside. Electricity, again, is going to be into there. It's going to be, basically rotating those poles. Sometimes the stationary magnets are on the rotor, and sometimes the stators, that's going to be these windings, these copper windings that are all on the outside. We're creating electromagnets on the inside of these things that are going to be stationary, and we have some that are going to be kind of rotating. But basically what's happening is we're basically changing those, around. We're allowing that stuff to basically repel each other to create that spinning or that turning force. You're going to have terminal boxes on here. You're going to have your drive shaft. This is probably one of the most important things because this is what's actually going to be driving the equipment that we have. We can put pulley systems on here. We can put chains on there. We can have something connected directly to that to get that spinning action. But that drive shaft is what's actually going to allow us to transfer that power into something else. So we're changing this electrical and the magnets that we have, and we're turning that into mechanical power that we're going to be able to use for basically all of our equipment that we have. Now, what's probably the most important thing when we're dealing with motors is probably the RPMs, or the revolutions per minute. Okay. And how fast a motor spins, okay, has to do with the hertz, which is basically the wavelength that we are dealing with when we're talking about electricity. Here in America, we deal with 60 hertz. In other places like Europe, they deal with 50 hertz. And I'll talk about that in just a second on how that kind of affects things. But we'll go and stop that real quick. And I'll show you guys a little something on hertz. When we think about electricity, okay, we're going to have wavelengths that are going to come by, and especially when we're dealing with like AC electricity. If we were to have a line, this would be kind of our 0 point. We're going to create a wave that's going to come up, it's going to come down, come up, come down, come up, come down, come up. How many times this thing goes up, down, and then back up and kind of hits that line, that right there is what we consider one. I'm drawing this upside down, aren't I? One, that looks weird, hertz. We measure hertz or we represent hertz with HZ. And that looks like some really weird writing that you probably can't read at all. But anyway, from this point here to that point there, that is going to be 1 hertz when that wavelength basically goes up and it comes back down. We can change the amount of hertz. Like I said, in Europe, we use 50 hertz. And so that's going to be, less cycles per second. We talk about hertz. It's how many cycles, how much this goes up, down, and then back up again. How much that does in 1 second, okay, is going to be 1 hertz. So it does this 60 times here in America. In Europe, those lines are going to be closer together. and you're going to have more of them. Actually, no, I take that back. We're going to be bigger, and we're going to have less of those wavelengths in 1 second. Okay. Now that's important because if you've ever gone to Europe and if you've ever, tried to like plug in like your cell phone and stuff to charge it, you can't charge your cell phone without having a special adapter. That's because our equipment is set up for the 60 hertz. In Europe, their stuff is set up for 50 hertz. Why? I don't know why we decided that, it works here and that's what we have. But you can't do that without having some sort of adapter that's going to adjust that to that 60 hertz, to like charge a cell phone or something like that. So the way that these hertz work, okay, it's an up and a down. It's basically got an up cycle. It's got a down cycle. We'll go back to this share screen here. So now some of these things, I know I'm kind of explaining probably a little bit more. I know I might be losing you. Some of you might be following along, but don't worry about this because you're not going to have to do this math. I just like to explain things so that way you have, a bigger understanding. But to figure out the revolutions per minute that a motor is running, we're going to take that 60 hertz. That's a constant. Okay. That's how many times it's going to cycle up and then down and then back up. Okay. That's going to happen in a 60-second period. Okay. So to figure out the revolutions, we're going to multiply those two numbers together. And then we're going to multiply that by 2. And that 2 is because it has both in one cycle, it's got both an up and then a down cycle. Okay. So it's got both of those things on both sides of that. That's why we're going to multiply that by 2. If we were in Europe, we would do the same equation, except we would take 50 hertz, we would multiply it by 60 seconds, multiply that by 2, and we would get a number. But when we do that, we end up getting 7,200. And it's important that is going to be a constant. And what we're dealing with here, everything I'm going to ask you is going to be dealing in 60 hertz. You're going to have that 7,200 number as a constant. If we take that and we divide that 7,200 by the number of poles, that is going to determine what the RPM of your piece of equipment is. So if we were to take 72 and we were to divide that by 2, okay, let me pull up a calculator so that way you guys can see that. If we were to take this 7,200 and we're to divide that by 2 poles, and every motor is going to have at minimum 2 poles because you're going to have a north and a south pole. Some motors might have 4 poles. Some might have 6. Some might have 8, 10, 12. They're always going to be even numbers, and it's always going to be a solid number. But if we take that 72, we divide that by 2, okay, if we had a 2-pole motor, that motor is going to be running at 3,600 RPMs, okay? So that motor is going to run at 3,600 RPMs. Now, just kind of a little fact, that's typically the speed that most motors, like the maximum that they're going to run at, because at minimum, a motor is going to have 2 poles. So here in America, 3,600 is kind of like the max speed that any of these motors, are theoretically going to run. There's some things that can kind of change with that. Now that is not under any load on that RPM. Okay. So there is no load on there. There's no friction that's being accounted for in there. And there's always going to be some friction because there's always some bearings. There's some things that these parts are moving on just in our ambient air. Okay. We are not in a vacuum. So we are going to have friction in pretty much every environment that we are working in. And you're going to have that kind of stuff. So when we add friction into that, or if we put a load on that, it's going to slow that motor down. It's not going to be running, at that speed there. But we can kind of run through some of these things here. If we have a 2-pole motor, oh no, I don't want to click forward. A 2-pole motor, we've got 7,200. That's going to be our constant. Okay, that deals with the hertz and seconds, right? And then how much it goes up and down. We divide that by the 2 poles that are in that motor, should get 3,600 RPM. Under a load, that RPM might be anywhere between 3,000 to 3,450. Okay, so you're not going to have this at 3,600 RPMs. Some of the nameplates that you're going to look at today, okay, and you're going to have to determine RPMs, you're going to have to determine poles on these things. Some of them are not going to have 3,600. They're going to have 3,450. You can take this same equation and you can work this thing backwards. If you know that 7,200 is a constant and you aren't given the number of poles that are on that motor, you could take the RPMs and you could work this equation backwards. So I could say 7,200. If my nameplate says it's 3,600 RPMs, I divide 7,200 by 36, and that's going to give me the answer of 2. It's a 2-pole motor. if I were to take that 7,200 and divide that by, let's say my motor nameplate says 3,450, I divide that by 3,450, and I'm going to get 2.0869. Doesn't matter, okay, when you do this, when you're working with these equations, understand that that's still a 2-pole motor. We are not concerned with all the decimal points that are past that, because a motor is going to have a north and a south pole, okay, and it's going to be in increments 2, 4, 6, 8. It's never going to have an odd number. You're never going to have a 3-pole motor or a 5-pole motor, okay. They're always going to be even numbers, okay. And when you're doing these, if you get the equations where it's like 3,450 or if it's 1725, okay, you're going to get a number that's going to have a decimal for it. Just give me that whole number. That's the answer. That's how many poles that motor is going to have. And I'm going to run through a couple examples with you when we go through and do the lab. A 4-pole motor, right? Typically with no load, it's going to be 1,800 RPMs. Under load, you're going to be 1,600 to 1,725. A 6-pole motor, right? Same thing. The speed is going to drop down. So the more poles that we have on this motor, the lower the speed is going to be when we're actually running these things. So what RPM, like which RPM do we need to use? It's really determined by the operation that needs to happen. Okay, so what job needs to be done? Okay, how loud or how quiet does the motor need to be? Okay, the faster the speed, the louder that motor is going to be. The most common one, and probably if not, most, but maybe even all of the motors you're going to look at are probably going to be a 4-pole motor. So you're going to be somewhere around these speeds of 1,800 to 1,600 RPMs. Okay. And you'll notice that there's a big difference in the drop on these RPMs here. They're not like, oh, they don't really like crossover. You don't have one that's like, yeah, it's a 4-pole, but it runs at like 3,000 RPM. No, if it's 3,000, it's a 2-pole motor. So the 4-pole motor is the most common. You can simply, without even having to do this math, if you go back to this slide here and you want to answer these questions, if you have the RPM, if the RPM falls within these ranges here, you can look back on here and say, oh, that's a 2-pole, that's a 4-pole, that's a 6-pole. You can do the math if you want, but you don't necessarily have to. They have designed 12-pole motors, which is, quite a bit of poles on these things. That's 6 different sets of north and south poles. And they've been designed for like washing machines and different stuff like that. So that way we have a quieter motor. It's not making a lot of noise. We want that. If it's in a house, we don't want this thing to be making a bunch of noise as it's running, because we want to be doing other things. In a shop, 1725 typically is a pretty common one, the 4-pole motor. They're going to be a little bit louder, but we're not concerned with that because we're in a shop, right? We're not worried too much about that. Now, sometimes we do have motors that are going to have variable speeds, meaning that we can kind of change that speed. We can increase it, we can decrease it. And if you kind of think to that math that we have, if we had 60 Hertz, we had 7,200, but if we change that Hertz and we increase that Hertz or we decrease that Hertz, that is going to have an effect on how fast that motor is actually spinning. And so what we do is we input a frequency controller into these things. And some of our drill presses are going to have frequency controllers that are going to allow that to adjust up and adjust down. You also see variable speed motors on pool pumps. Okay, a lot of pool pumps are going to have variable speed motors to where you can, decrease that. You can have that motor running really low. It's going to be really quiet. It's not going to use as much electricity, but it's still pumping water within a system and basically cycling that water through. If we want to cycle that water through quickly, we essentially just increase that Hertz in that motor. It's going to increase the speed of it, and it's going to pump more water through. And sometimes on like pools, especially, what we do is we run it real high at a high speed at night when nobody's running electricity, when the rates are a little bit cheaper. And then when, the rates kind of get a little bit higher, we tend to kind of drop those speeds down. So that way we're using less electricity during those peak hours, and we can save some money on these things. So we do have the ability to kind of do that. Some of the things that we're looking at, and we're not necessarily going to look at all of these things, but things that you can find on the nameplates, is the Hertz that we have, the voltage that's going to be input. These are going to be pretty important. Hertz, for the most part, they're going to be the same, right? Here in America, it's 60 Hertz. You want to make sure that you match it and that motor does run at 60 Hertz. You're not buying something from Europe that's set up for 50 Hertz and is not going to operate properly here. You want to know what phase. Is it single phase? Is it 3-phase? Okay. Most of your houses are all going to have single phase, and shops where typically might have some 3-phase stuff that we're going to plug into. And you can't just interchange those things. 3-phase power is a little bit more efficient on the power. They have, 3 different hot wires that are coming in, as opposed to the stuff that you guys have been wiring in class or the diagrams that you've been wiring. Those are all single phase, wires where you have one hot wire coming in, and that's pretty much it. Those are all going to be kind of single phase. We do have 240 volts where we could have 2 hot wires coming into it. It's still going to be single phase. But a lot of shops, they're going to have this heavier duty power. They're going to have that 3-phase power. And you got to make sure you match those things up, right? Duty cycle is basically just how long that motor can run without having to have a rest. So some motors you might be able to run in a 10-minute period. You might be able to run them 6 minutes and they need to rest for 4 minutes. So they have this cool down period. A lot of the motors that we have on the equipment in the shops that we have, they're going to be continuous motors, meaning, and they're going to have the words CONT on them. They may not say continuous on there. That's going to be CONT. And what that stands for is just a continuous motor. It means that it can run without having to have any kind of rest period. So the cooling effect that motor has and the power that's basically using, it's not going to overheat that motor as you're using that stuff. Horsepower is important, right? You got to know, you got to be able to match up that horsepower so that way it can do the right work. If you have a 3 horsepower motor and you try to replace it with a 1.5 horsepower motor, you're going to be severely underpowered and that thing's not going to work like it should. Ambient temperature just has to do with where can it be, at. This is not something that we're really typically, worried about when we're replacing them. They're pretty standard, a lot of those things. And the other one is like, what type of insulation does it have? Is this something that's going to be submerged into water? Is it something that's going to be in a moisture-free content? The insulation is going to basically determine, where it's used at is going to determine what type of insulation we have. So you may have some of those other factors, but maybe, let's say it's something that needs to go underwater. You don't want to put a motor that's underwater that has all these other factors, but it's not designed to go underwater, doesn't have the insulation. You wouldn't want to do that because they're going to fry circuits, maybe cause a fire or something like that. So it's important to understand those different things. So on the nameplates, these things are, this is kind of an example of, an electronic version of this, but they're going to have tons and tons of information. Some of this stuff we're not worried about, we're not concerned with, but the biggest things, kind of the voltage, we're worried about the horsepower. You can notice that's represented in HP. When we have this thing called duty cycle, okay, that is basically the time that it can run. Okay, so the duty cycle, it might say duty on there. It's going to talk about that. And that is going to be, like I said, on most of them, it's going to be continuous. They can run continuously. You don't have to shut those things down before it burns up. You can see the RPMs, right? You can see the pH, that's the phase. Okay, so they may have a 1, they may have a 3. Those are really your 2 options on the phases. They have frame design, things like that. I'm not worried about that. Manufacturer's type, model numbers, serial numbers. They've got all those things. Those are pretty basic. I don't think I have any questions that are going to go over those. But it all is going to be able to be found on this plates, and every motor is going to have these nameplates that are going to be on there. Here are some real life examples of some nameplates that we can find on things. On some of these, you might notice that like on this one, it has volts. It has 208 to 230. That's just kind of a range that it can go into. You can find the RPMs. This one's a 3450. That's going to be a 2-pole motor if you do the math. Our phase is just a single phase. We're not worried about class. We're not worried about that other stuff. Where is my duty cycle at? Should be on here. Rating. Okay, I think it's under the rating here. So this is like the 40 degrees Celsius ambient temperature, and it's a continuous motor. So sometimes they're not all the same. You might go over to this one. You might see something that is maybe a little bit different. Okay, this one's got the rating 240, right? And the continuous motor right there. This one's a 3-phase motor. This one's a little bit different, and you're going to encounter some things that are like this, where we have 208, 230 volts / 480 volts. You'll notice our amps, it's either 14.8 to 14, or it's 7 amps. Okay. Now, a lot of motors have the ability to basically change that connection on here. So we can actually take these wires from the inside and we can change how those wires are connected, and we can wire it for a 208 or we can wire it to a 480 volts. So you can kind of flip flop it. Depending on what type of power you have input, you can match that motor to that. And so some motors are going to have the ability, okay, depending on how the windings go and stuff, you can kind of change those.